All right, good morning. So, what I want to do today is to finish out chapter 23 and try to give some context to all this stuff with AC circuits. So, just to recap, what we learned yesterday is that when dealing with AC circuits, we can avoid a lot of the annoying dealing with constantly shifting currents or voltages and the sinusoidal dependencies on them by instead talking about average values or RMS values and inventing quantities called reactance and impedance that allow us to treat resistors and capacitors and other things whose responses to an AC circuit are time varying and to treat them in a more aggregate fashion. And so that's fine and dandy. You can figure out a lot. But there are times when maybe you want to know what exactly is the current at a particular moment, or what exactly is the voltage in the circuit at a particular moment. So it's important that you know how to do that. And it's very easy, but it does mean that you'll have to do some conceptual thinking sometimes in order to figure your way out. Um, so let's talk about that for a second. Wrong share. Oh, stupido. There we go. Methicam. There we go. So let's imagine that we've got an RLC circuit and it's driven by some voltage. Let's say that we've got 12 volts AC, and that's driven at 60 hertz. I got a resistor, capacitor, and an inductor. And let's say that the resistor is 10 ohms. The inductor is 5 millihenries. And the capacitor is, hold that thought, sorry, I lost my calculator. I had to go grab it. All right, let's try that again. So the capacitor is, let's say, something like 80 microfarads. And so what I'd like to know is what is the instantaneous current and voltage uh, at some time, let's say 10 seconds after we hook this up. Now, in order for me to do this, I'm going to have to know a little something about what the conditions were. So we need to know a little something about what the conditions were when we started. And the reason that's important is because remember, every quantity in this circuit, the current, the voltage, that sort of thing, is going to be sinusoidal in nature. And, you know, if you've got a sine wave, it's going to look like this. If you've got a sine wave that's phase shifted, then what's going to happen is it might be, you know, more like this. Right? Where the entire thing has shifted some amount either to the right. I could also shift it to the left. Notice that if you shift a sine wave far enough, if I just shift a sine wave far enough, it can turn into a cosine wave, right? This is just what you get if you shifted this a full 90 degrees. So oftentimes what's important is you've got to specify something about your initial conditions in your circuit. And traditionally, what typically happens is you start your timer, you start your stopwatch in such a way that the current is equal to 0 at the moment that you start. And in fact, you do it in such a way that traditionally that the current can be written with no phase shift. So I can say the current equals I max sine omega t. If I do that, then what's going to happen is my current graph would look like a regular sine wave. And at time 0, it would start out at 0. Now, you don't have to make that choice. It's entirely possible to choose something differently. And in fact, one of your homework problems does the exact opposite. And it chooses to start where not the current equals 0, but where the voltage equals 0. And we'll deal with how to correct for that here in a little bit. But for the moment, we have to choose something to proceed with. Let's proceed under this assumption that my current at time 0 equals 0. Now, what that means, though, is that unless the current and the voltage supply are in phase, the voltage supply won't necessarily peak at the exact same moments as my current. So my voltage may be shifted to the left or to the right by some amount. And so in order for us to figure out the instantaneous voltage, we're going to have to do a little bit of work. And we'll have to start that process the same way we did the problem yesterday. The first thing we'll do is we'll figure out for these conditions what is my impedance and what is my I max. So usually AC voltages are reported in terms of RMS voltages. So this 12 volts is the RMS average voltage. From that, I should be able to find the RMS current. So let's do that. Let's start off by finding the impedance of these 3 elements at that frequency. Well, first, I've got to find the capacitive reactance, X sub C. And I know that that's 1 over omega times C, or 1 over 2 pi F times C. And in this problem, the F was 60 hertz. The C was 80 microfarads. And I can crunch those numbers. And it turns out that at this frequency, our capacitor is acting in the same fashion as a 33.17 ohm resistor. Now, what about XL? That's my inductive reactance. Well, XL is equal to omega times L, which again is going to be 2 pi F times L. So 2 pi times 60. And L is 5 millihenries or 0.005 henries. And so it turns out that the inductance is only about 1 ohm. It's very small. Excuse me, so the inductance reactance, not the inductance. Of course, R was 10, so I can find my impedance. Excuse me. I'm having a rough morning. Ugh. So remembering that R is 10, I have 33.17 minus 1.885 is 31.285. I square that plus 10 squared. Then I square root that. That's a 4, not a 9. So the entire impedance of this circuit is about 32.84 ohms. So once we know that, what do I do with that information? Well, I know that I can use Ohm's law for AC circuits, which says that V equals I times Z, the impedance. And since I'm given the RMS voltage, if I use this, I'll be finding the RMS current. So the current I can get from that. And of course, the RMS current was given to be 12 volts. So in that case, I'm going to have an RMS current of about 0.3654. Notice I'm keeping 4 sig figs because I usually like to round down to 3 at the end, but I always keep extras along the way. And we have a lot more math to do. So now I know the RMS current. Now, my expression for the current as a function of time is in terms not of the RMS current, but of the maximum current. So I need to know I max. However, I recall that the RMS current is always equal to the max current times the square root of 2 over 2. So if I just rearrange this, I can find the maximum current easily enough. Current, it turns out, is going to max out at a slightly higher value of about 0.5168 amps. So if I wanted to know the instantaneous current 10 seconds after I start, then what I would have to do is, I know that the current at any given moment is going to equal whatever I max is times the sine of omega t. And that's I max. So I can just plug in. Of course, omega again is 2 pi f again. So 2 pi times f, which is 60, times t, which was 10. And that's going to put out a value for myself. Now, here's a caution. And this is something that screws up a lot of students. You'll notice that I have a sine function, right? But I'm not taking the sine of an angle, right? The thing inside my sine function is a time times an angular frequency. Now, time has units of seconds, and angular frequency has units of 1/seconds. So the units of this thing cancel. And that's important because anytime you take the sine of some sort of function, the argument of that sine function always has to be dimensionless. However, degrees are not dimensionless. So what it means is that if I'm taking the sine of some physical quantity that's not an angle, my calculator needs to be in radians mode because I have to take the sine of this many radians, not that many degrees. So if you're in the wrong mode, you're going to get the wrong answer for these questions. So make sure that you put your calculator in radians mode before you do this calculation. Otherwise, terrible things will happen to you. So now that I'm in radians mode, and I crank all that, let's make sure that's like, I end up getting a negative value at that moment, negative 0.00164 amps. Now, why is it negative? Well, remember that this is a sine wave, right? And there are plenty of times when the current is traveling forward. We just happen to have picked a time that occurs during one of the negative sweeps. And notice it's negative, but it's really, really tiny. So what that tells me is that we picked a point that's very, very close to here rather than down here. It happens. Now, that gives me my instantaneous current. But what about the voltage, right? My power supply is also alternating back and forth, but because of the effects of the capacitor and the inductor, the voltage supply may be out of phase with my current. And so this is where we have to know what is our phase angle. By how much does the current lag or lead the voltage? So we can figure that out. We learned how to do that last time. We know that the tangent of my phase angle is going to end up equaling XL minus XC over R. And for this specific example, if you recall, XL was very small. It was only 1.885 ohms, whereas XL was quite large, 33.17 ohms. And the R was somewhere in between at 10 ohms. So if we're looking for that phase angle, it's going to be the inverse tangent of all that stuff. And so when I crunch that in, 1.885 minus 33.17 is going to give me a negative numerator. I'm dividing by that by 10, I'm getting negative 3.1285. And I take the inverse tangent of that. Now, again, this is one of those places where we want our answer to end up being in radians. So I'm leaving my calculator for the moment in radians mode. And I find that we have a phase shift of negative 1.26 radians. And that's annoying to me because I don't usually think in radians. So, you know, that's it's not immediately obvious to me what that means in degrees. However, I always can convert from radians to degrees because I know that 2 pi radians equals 360 degrees. So if I divide that by 2 pi and multiply by 360, in more familiar units, it's a phase shift of negative 72.3 degrees. So that at least makes sense to me. But this is what I'm going to have to use in my actual calculations. They're the same thing. Notice that I have a negative phase shift. So what that means is that in this case, because I have a negative phase shift, it means if you're looking at your phasor diagrams, right? Here's VR, here's VC, here's VL. My phase angle is down here like this. And so what that means is that my current, which is always in phase with VR, is ahead of my V total. So in this case, what we would say is because this is negative, we would say the current leads the voltage. And so what's going to happen is if I want to write an expression for my voltage as a function of time, it'll always be Vmax sine omega t, and then I have to add or subtract that phase shift. Now, since we're doing this expression and we're referencing the current, like the current is our frame of reference. We're always referring back to a current with that starts at 0. And what's going to happen is if my phase shift is negative, all I've got to do is just add in that negative value. So in this case, it'll be, you know, minus 1.26 here. Notice, however, that you don't necessarily have to start your timer when the current is equal to 0. We could have instead said, no, I want the voltage to be 0 at time 0. And if that was the case, the current would have been shifted relative to the voltage. And one of your homework problems does exactly that. It says, no, I want the voltage expression to simply be V equals V max times the sine of omega t. But if that's the case, your current is going to equal I max sine omega t plus or minus some phase shift. So in our case, we chose to have the straight up sine be the current and the voltage was shifted. In other problems, you may have the voltage be the one that you're using as your reference and the current would be shifted. Notice, however, that if this were the case, if I'm shifting the current, well, if the voltage leads the current, that's the same as saying that the current lags the voltage. So doing it one way, we put it in like minus 1.26 here. If I had been shifting the other way, I would have flipped the sign and made it positive. So bear that in mind when you're working through these problems, is that, you know, depending on what you're referencing, you'll want to pay attention to whether the voltage leads or lags. And that will determine the sign of this phase shift. Because I'm using the current as my reference, I had a negative phase angle, I put in a negative number. Had I been using the opposite convention, I would have said, aha, if the voltage lags the current, then the current leads the voltage, and I would have put in positive 1.26 had I referenced it the other way. It doesn't matter as long as you know what your references are. And most of the time, a problem will specify something about what your initial conditions are, and that'll help you know which of those two conventions you should adopt. So at this point, it's all over but the crying, because all I've got to do is calculate that. And again, I've got 2 times pi times 10 seconds minus 1.26. I'm taking the sine. Again, I'm still in radians mode of that. Then I'm multiplying that by Vmax. Oh, but wait a second. What is Vmax? Well, if we know that VRMS is 12, then Vmax is going to be 12 divided by square root of 2 over 2. So it'll be slightly larger. About 16.97. So now if I plug that in here, this is Vmax. I get that the instantaneous voltage ends up being like negative 16.16 volts. So one thing I'll caution you, you do have a problem that's kind of like this for your homework. And one of the things that's difficult is, since omega depends on pi, you want to be a little bit careful. This function, the sine wave, has such a short period that even tiny little changes can affect your answer in a big way. So like when I calculated this value, I carried out pi to a whole bunch of digits and did it that way. If you round off too much, that can make this problem highly susceptible to round off error. So be exceptionally careful. Otherwise, your answer may vary considerably from the expected values. So, this is one of those things that you should know how to do it. Very rarely will you ever need to know the instantaneous value of a current in a circuit. Usually we care more about the average values, but it's certainly something you should be prepared for. It's not hard. It just requires a little bit of common sense to know how to deal with the phase shift and the ability to break down the impedances the same way you would do if you were dealing with average values. So it's tedious, it's long, but it's not hard. Awesome. So the other thing we have to address regarding AC circuits is, why on earth do we use AC circuits to begin with? Like, what's the point of using alternating current rather than direct current? And it turns out that this is not an answer that was immediately obvious to the people who were inventing it. It was the sort of thing that actually grew out of a long and protracted debate over which was superior, alternating current or direct current. A year or two ago, there was actually a movie about it called The Current. It was pretty cool. It had Michael Shannon as George Westinghouse, who was one of the early proponents of alternating current. And it had Benedict Cumberbatch as Thomas Edison, who was one of the early proponents of direct current. And the reason it was such a big debate is because back in that era, as people were first learning to adopt one kind of current or the other kind of current, uh, building the ability to have power plants that supply cities that are putting in things like electric lighting around the cities was difficult. And one of the early challenges that Edison and his direct current uh, technology had to deal with was, how can you have a power plant and send power over usually several miles to electrify a city that's far away, or even multiple cities down the line? And the reason it was challenging for Edison is because of something like this. You see in the movie, they don't talk about it in much detail, but the idea is simple. Imagine I have a power plant. So I can think of my power plant as kind of like a big battery. And maybe over here, here's your house, or here's a city. Now, if I want to send electricity using direct current to your house, I'm kind of treating your city or your house like a resistor or a set of resistors. So conceptually, that's kind of what your house is doing. And I've got to send current in one big circuit to your house and from your house, right? That's what's happening in a DC power plant. Now, the issue is that normally, if I'm dealing with wires going from my battery to my resistor, normally the resistance of those wires is so small that I don't even really care. I pretend like they have no resistance, and life is great. Unfortunately, if that wire is several miles long, I can't really get away with pretending like it has no resistance. In fact, in reality, it's going to have a resistance on the way to you and a resistance on your way back. And that's important because remember, the resistance of a wire is rho times L over A. And L is really huge. And that's why R ends up being measurably large, even if it's normally something I can ignore. And here's why that's important. You're sending current out of your power plant, and the problem is every bit of current that you get to this house has to travel along the way through that resistor. There's no other way to get the current from the power plant to your house with direct current. And what that means is that as the current travels through that resistor, there's a voltage drop, right? You're burning energy just to get the power to your house. How much power? Well, we had 3 formulas for power, right? But one of them was power equals I squared times R. And remember, since I have to send all the current for the entire house, or heck, for the entire town, has to go through this section right here. Well, and the power that it takes to just get it through here is I squared times R. Every time you double I, you're quadrupling how much power it takes. It's taking a ton of power just to get it through the power lines. And that's not power that the house can use. That's power I'm wasting just getting the energy to you. So what sucks for Thomas Edison is that his technology doesn't work very well if these power lines get very long. And so it means he can't just have one power line or one power plant and then send it to several cities down the line. He can't have that power plant supply several hundred miles worth of area. He's instead got to build a ton of power plants, basically really close to the cities. They can only go a few miles before he doesn't have enough power left over to generate much in your towns. So this really sucks for Edison, right? And he's trying to convince all these municipal governments that, his power is the one to adopt, when he's got this big technical limitation that he doesn't have a way around. Now, the other side of this current war is a company called Westinghouse. and a guy named George Westinghouse. He ended up working with Nikola Tesla, the guy that we named the unit of magnetic field after. Tesla was an immigrant from Serbia, brilliant guy, a genius in terms of alternating current, but apparently he had like really bad money problems his entire life. And he worked briefly for Edison, and Edison ripped him off, or at least he felt like he ripped him off. And so he, quit in disgust, and the two of them were sort of bitter enemies for the rest of Tesla's life. But the upside is that if you're dealing with alternating current, there is a potential solution to this issue. And here's how it's going to work, right? Imagine that you're building an alternating current power plant. What you're going to do is you're not going to connect your power plant directly to the cities at all. Instead, what you do is you take your power plant and you put your AC generator, which is like your battery, and I've got a circuit. But what's going to happen is that circuit doesn't connect all the way to the house. Instead, what it does is it connects to a coil. Now, what's going to happen is this coil has inductance, and I'm sending an alternating current through that coil. That means that inside that coil, you're generating a magnetic field, but every time the current flips direction, the magnetic field is also going to flip direction. And changing a magnetic field inside a coil creates a back EMF. So there's going to be a voltage from Faraday's law across this coil. And what that means is that the voltage of this pushing back against the battery is going to keep the current very, very low. So there's very little current traveling through these power lines. And that means that since there's very little current traveling through the power lines, the amount of power lost in the resistance of those power lines is relatively small. By making this, 100 or 1,000 times smaller, well, 1,000 squared, oh my God, that's 100,000, right? That's 100,000 times less power I have to waste getting from here to here. But I still have a huge voltage across that inductor. Problem is, that doesn't help the house at all. So here's what you do. The house, which again is kind of like a big resistor, is connected to a second coil. And what you do is you put this coil inside the other coil. So the two coils are either nested into each other, or sometimes what you'll do is you'll have coil number one surround a piece of iron, and then coil number two wrap around that same piece of iron. Now, why iron? Because iron is ferromagnetic. Now, what does that mean? When you turn on the magnetic field in this coil, it tends to magnetize the piece of iron. The magnetic spins in the piece of iron tend to line up with the magnetic field, but every time the magnetic field in my coil switches, the magnetization of the piece of iron will switch with it. And so my iron is basically turning into a permanent magnet whose north and south poles keep switching, which in turn is creating a magnetic field inside the second coil, which is also switching. And that means that I'm generating a voltage inside that second coil. And that voltage inside the second coil can now send current the rest of the way to the city. Now, the reason this is useful is because what you can do is, I want to transmit power from the power plant to the house. And we have three expressions for power. One of them is I times V. And we already said that by having this guy push back against the battery, the current is quite low. However, even though the current is super, super tiny, we can crank the voltage up ridiculously high. So what you do in an AC power plant is you generate your power at some enormous voltage, tens of thousands, hundreds of thousands of volts. And even though the current is super, super tiny and you're barely losing any energy at all inside your power lines, you are generating a huge voltage over here. Now, the issue is you don't want to have 100,000 volts inside your house because, oh my God, what happens to little Timmy when he sticks a fork in the light socket as a 3-year-old when it's 100,000 volts? Jimmy's going to be incinerated, right? We don't want to have that happen. So we need to keep our voltages safer in the household. So what you do is you modulate the number of turns of wire in these two coils. Because what's going to happen is the voltage generated in this coil is going to come from Faraday's law. It's going to be equal to the rate of change of flux per time. And if I have a certain amount of flux in each loop, I can multiply that by how many loops. So what's going to happen is the voltage here is going to be dependent upon the number of loops. The voltage here is going to be dependent on the number of loops there. And so what's going to happen is you will find that if I have two coils, I should probably adopt the naming convention. If I call this the primary coil and this the secondary coil, what's going to happen is the voltage in those two coils is going to be in ratio to the number of turns in each of those two loops. And so imagine what happens if my primary coil has some ridiculous number of loops, like 10,000 loops. But imagine that my secondary coil only has 10 loops. Now, what's going to happen is if I solve this for the voltage that I get in my household, so again, what did I do? I took this expression here. I wanted to get V secondary by itself. So I multiplied V secondary on both sides. And then I multiply by this on both sides, divided by this on both sides. That's why these flip. This is on the bottom now. This is on the top now. And you'll notice that what's going to happen is the voltage I get in that secondary coil, the one that's connected to my house, is going to be whatever the primary voltage was times the ratio of this number of loops. And in this particular case here, what's going to happen is this is only 10, whereas this is 10,000, right? Which means this ratio is 1 over 1,000. So my secondary voltage is going to be 1/1000th of whatever the primary voltage was. So if I'm putting my primary out at, let's say, 100,000 volts, then what's going to happen is my secondary is going to come out at only 100 volts. So inside my secondary circuit, I have a way lower voltage, but I make up for it because I'm transmitting the same amount of power. I made my voltage go down by a factor of 1,000, but the amount of current that I'll have available is going to be 1,000 times more. So I can have a lot more current that I can send to all the different houses in the town and not have to do it over a very large distance. So I'm able to over large distances transmit at large voltage, but a tiny current. And then once I get near my destination, I use this device, which is called a transformer, to shift. And in this part of the circuit where I'm at short distances and I don't care about the resistance of my wires, have a huge current but a tiny voltage. And that's how Westinghouse was able to build power plants much more efficiently than Edison, because he didn't have to worry about the distance so much, because he could use transformers when he got close to his destination to transform very high voltage AC into lower voltage but higher current AC. And ultimately what happens is AC wins this fight, right? Alternating current is the standard that we adopted because it was so much easier to solve this problem. So transformers are useful for like that. They, by changing this ratio of coils, you can either increase or decrease the voltage in your output compared to your voltage in your input. Now, what I've drawn here, where I have a lot of coils in my primary and comparatively few coils in my secondary, is what we call a step-down transformer. And that's the kind of thing that would be useful in power development. But there are other situations where you might want to have a step-up transformer, where you put voltage in that's low and it comes out at a higher voltage, but of course, comparatively smaller current. How would you do that? All you'd have to do is make the number of loops in the secondary larger than the number of loops in the primary. That's pretty cool. Now, you've certainly used transformers pretty much every day of your life, because frequently what happens is, you have to step up or change voltages for various applications. And in fact, I've simplified this process even for power supplies, because typically what happens in a power plant is there's not just one transformer, there's often a series of several. Typically what will happen is your power plant will end up generating your voltage at hundreds of thousands of volts. Those hundreds of thousands of volts will then travel cross country in the very, very, very tall, high energy power lines that you might see out in the middle of the field somewhere far from cities. Then they'll arrive at a substation. And so this might not be your house, it might be a substation. And that substation will use a step-down transformer to step 100,000 volts down to something more manageable, like 10,000 volts, or even 1,000 volts. Then that substation might then go to a neighborhood substation. And you see those sort of around, they're usually fenced off. That neighborhood substation might go from 10,000 volts down to a few hundred volts. And then that goes out to your individual neighborhood. And if you look at the top of light poles inside your neighborhood, you'll often see these little round, often green objects. Those are transformers. And inside those transformers, what it typically does is it will step down a few hundred volts to 120 volts. That 120 volts goes directly to your house. And that's why your house is powered at 120. And then, of course, even within your house, sometimes you'll use transformers. Right now my computer is plugged in, but it's plugged in to the wall at 120 volts. But my computer only takes 12 volts. And so this, inside this box, is a transformer. And what that transformer is doing is it's taking the 120 volts coming in from the wall, it's stepping it down into 12 volts. It's all rectifying it. It's turning the AC into DC, but that's a whole other story. And 12 volts is what goes into my computer. If you ever travel to Europe, you want to be careful, because Europe uses a different standard voltage. They use I believe it's 220 as their standard voltage. And what that means is that if you were to take your laptop to, say, Paris or something, and plug your laptop directly into the wall, you'd be putting in 220 volts to a device that's only expecting to get 120. There's some stuff that's going to melt. You would destroy your computer if you did that. Fortunately, what you can do is you can buy adapters. And what are those adapters? They're just transformers. They're transformers that take 120 volts out and or to 220 volts out and converts it into 120 volts. So that's how transformers work. Usually that's really all you need to worry about, is that the ratio of the voltages in the two coils will always be the ratio of the number of coils. I should also caution you that this transformer only works so well as if the flux between the two objects is shared. That's why we use this iron core, so that as much of the magnetic field of this as possible also goes through this. Otherwise, they wouldn't match. The other way to pull that off is to literally have one coil inside the other. That maximizes the amount of flux shared between the two coils, so that the two voltages match as nearly as possible. The other issue with AC that you're going to have to tackle is the issue of power. And in an AC circuit, power can be a little bit more complicated than it is in DC. In DC, we always started with P equals I times V. But remember, what's going to happen is that in an alternating current circuit, the voltage and the current are not necessarily in phase. And so what could happen sometimes is there could be moments when, if you're looking at your resistor and you've got current going through it, it could be that at that moment, the voltage across your resistor is quite large. The voltage being put out is quite large. So V is huge. But at that moment, when the V is huge, there's hardly any current coming out. And that means not a lot of power being delivered. There may be other moments when I have tons of current going out, but the voltage is super, super tiny. I'm not going to get much power that way. Conceptually, the way to think about that is, remember, current is kind of like counting how many electrons go past you. And the voltage is counting how much energy each electron has. So if you have a high voltage but a low current, it means that every electron that's coming out of your battery has tons of energy, but there's hardly any electrons coming out. And that means not a lot of power being delivered to you. If you've got a high current but low voltage situation, it means there's tons of electrons coming out of that battery, but every electron has barely any energy. So if you want to maximize how much power you're delivering to your circuit, then what you want is for the moments when you have lots of electrons coming out of the battery to also be the same moment that every electron has a ton of energy. So what's going to happen is the power delivered in an AC circuit is going to depend on the phase angle. So if that phase angle is 0, that means that the current is always big at the same moment that the voltage output is also big. So I'm putting out lots of electrons, and every electron has a ton of energy. I'm going to get a lot of power out. And of course, if the angle is 0, the cosine of 0 is 1. And it looks just like regular multiplication at that point. If, however, my current and voltage were 90 degrees out of phase, the cosine of 90 is 0. Because that means that when I've got a ton of energy per electron, I got literally no electrons. So we call this the power factor for AC. And notice the power factor is going to be at its maximum when the phase angle is 0, but the phase angle is 0 when I'm in resonance. So I will get the max power when I'm operating at the resonant frequency. Remember, the resonant frequency was 1 over 2 pi times the square root of 1 over LC. We did that the other day. The other thing that I should point out is that if I'm using this power calculation, both I and V need to be the RMS values. You can't put the peak voltages or the peak current in. It's got to be the RMS values. But that's how you calculate the power being generated by an AC circuit. And again, that's, it's trivially easy, but super important. So hopefully at this point, you guys have kind of a handle on what's happening in an alternating current circuit. In most ways, it's very similar to what happens in a DC circuit. We just have to learn how to deal with frequency dependent issues like the impedance or like this power factor. But in all other respects, they're just like DC circuits, and hopefully pretty straightforward. All right, how we doing? Any questions?
No.
Okay. How's the homework looking, folks?
Everything's looking good on my end.
Okay. All right. Well, I don't want to start waves today, so I'm gonna say sayonara and sign you out.
Oh, the other comment, is the test being posted today? Or?
It's gonna be posted hopefully today. If I don't finish it, it'll be posted tomorrow. But it'll be. I'll give you 48 hours either way.
Okay.
Yeah.
Thank you.
You're welcome.